Yeah, so we're going to be giving an update on, as Peter said, on Barracuda product, where things stand, recent releases and some of the research that we're doing, and some of the recent, I think, improvements from a support and training standpoint. It's the green button? Yeah. Okay. All right, yeah, that's that. So, I don't know if I need to do much more of an introduction for the team. Rajat did a fantastic job yesterday introducing everyone. But this is our development team. We do handle everything from research, identifying what types of new models, features should be put in, and then looking at that from a implementation standpoint. How do we calculate these things in an efficient way? How do we make them usable? And then from a support standpoint, how do we best communicate that to the customers? How do we train them? And then get that feedback. We work very closely together. I think that's one of the advantages that we have here. For the R&D piece here, really what we're looking at is how can we expand the application areas of Barracuda for either existing industries that we support. How can we make Barracuda a more useful tool, and for new industries, new applications, what additional functionality is required to really have a usable engineering tool. And once we have that, then really the question is, okay, how do we do it fast? How we get these calculation speeds so that we are able to get results on an engineering timeline, and the domain sizes that are needed for some of these really complex systems, and then of course the usability piece. We want to have a tool here that is easy to use. You can get models set up quickly and with few mistakes in them, and get results in a short period of time. I want to take the opportunity here to talk about, from an R&D standpoint, particle physics. We've done a lot in the last few releases, but I wanted to focus in on some of the capabilities that are new. Some of them are actually quite old, but we get questions about them from support, and this is really in drag models, particle-particle collisional models that we have in Barracuda, as well as then this new bubble breakup and coalescence. And the reason, it's obvious here. The particle physics. This is the foundation of all the calculations. The reaction kinetics, heat transfer, these things are floating on top, and I think as Raj brought up this morning, you got to get the particle physics right, and so that is what I want to talk about here. Just to be very clear about this, so particle drag, we're talking about here, this is momentum exchange between fluid and the particles. Particle-particle collisions, or kind of these interactions, there's really looking at momentum exchange between particles and how they interact with each other. And then final thing is bubble coalescence and breakup, or other changes in size of particles, either size or number of particles within the system. And for drag, I think I'll just get right into it. For recent releases, we've added quite a few new drag models, or new to Barracuda, let's say, that are built in. For a long time, we've had a drag parser where you could implement models that were not built in, but and we get requests for, hey, I want to use this model, and we say, okay, yeah, we can put it in. It's a little bit computation, a little bit faster to use a built-in model, but of course, the side effect from having all these extra models is you get the question, well, which one should I use? And this is, this drag's kind of a funny thing in that there is, I don't know, at times, like personal feelings that come into drag models. And so what we wanted to do, though, and this has been a project that's been going on for quite a while now, is to kind of gonna go back and looking at, I would say, really kind of foundational data sets in drag models. And so this is from looking at data sets that used by Wen and Yu in the famous paper from 1966, where they pulled in their own data plus there's data sources like Willem and Kwok and Richardson, Zaki, et cetera, and went through these papers and pulled in bed expansion data that was used to do this fit, to determine this exponential constant in for the Wen and Yu drag model. And we, and the goal here was to be able to use this to look at error on other drag models. If you're just putting it through the same data set that was used to determine, or is the basis for this Wen and Yu drag model, which is really one of the, I think, still a very famous drag model, is used in still quite frequently, and is as part of a Gittesbau model. It's still around quite a bit, so assembled this set, and this is all liquid solid bed expansion data, right? So you get, and the data sets look like, okay, we've got some particles, it's in a column of some diameter, hopefully significantly larger than the particle sizes, but not always. And flowing some liquid through it, and you see how high this bed is expanded, and this is this is reported in this data. And so we went through the same analysis on this with this data and reproduced the same curve from the paper here, and it's pretty close. There's some points that are in the paper, and I can't find them. I don't know where they came from, but we're pretty close. And we see, make sure, in this paper they report voidage error of plus or minus 10%. And we see that for voidage, see about the same thing. The problem, though, is that voidage is kind of sneaky in that we've got it to some negative exponent here. So when we actually look at errors in drag force, they're quite large, more like plus or minus 50% for this data set. And but okay, so this is interesting. But then the question is, then what are we doing with this? And the original, actually, the goal of all of this was work we were doing to try to develop a yet another drag model. I guess the world doesn't have enough of them, but one that we could take minimum fluidization data and use that as an input into the drag model. And so from these data sets, it separated out into we had this full data set, and then there was curves where there was a defluidized region, so just kind of packed bed pressure drops, and be able to use this so we could determine what minimum fluidization velocity was for those particles. And it's really a good validation of the data, because otherwise you're just, oh, this is the diameter, this is, they say, it's sand or glass or lead shot or whatever it is, but there's, the question is how much of the errors that we see here is this errors in drag models, or is it just kind of scatter in the experimental data? So this was, this is the goal, and someday I'm going to maybe finish this paper. I've been talked about this at a few conferences and stuff, but this group want to talk about the Beatstra drag model. When we look at the amounts of error in these different drag models we have here, on what I consider is probably the more quality data sets here. Beatstra, I think, is quite good. And so this is for, if you don't know anything better, I think Beatstra is a good starting point for a drag model. For spherical-ish particles. For non-spherical, though, there are other drag models you can use. And like, so I just want to have an example here. This is, let me see, is this? Hey, okay, we got a video. We've been doing work recently with a company called Molten Industries. They're developing a methane pyrolysis process for decarbonizing steel production, and there's plans to model many parts of their system. But as a start, we just wanted to model this little cyclone that they have as part of their process, and because the goal, I guess in this case, is not necessarily 100% separation of the carbon from hydrogen. And what they have coming out here are some flakes, and they're quite non-spherical. And we didn't have much more information beyond that. And so the approach here was to use some bulk density data that they did have at Close-Pack and use, go back to this very famous paper. I spent a lot of time with the When and You paper. Look at data on a minimum fluidization or voidage at minimum fluidization versus sphericity. You say, oh, okay, based on this data, we think we've got a sphericity of this range. Put that into the drag model and run the case. And this was like right out of the box. This was very first simulation, no tuning. We get very good agreement with PSDs, both coming out of the top and the bottom of the cyclone. And the efficiency here was like dead on. It was within 0.1% of their measurements. So, so Beatstra recommendation. Beatstra accepted. You got cases where it's maybe more dilute, and single particle drag models, non-spherical particles. Maybe you have to take a different approach. Last thing I want to talk about in terms of drag is the subgrid modeling, and this is this can become important at larger scales where we start ending up we simulate systems with rather large cells in them, and at that point, as the cell sizes become large enough, we can't really assume anymore that the particles within these cells are uniformly distributed throughout that cell, and that the particles are going to see a local voidage that is the same as the cell average voidage, and the local velocities are the same as. And so this has been there's various models for this. In Barracuda, we've had an EMMS model for quite a few years that accomplishes the same, or is trying to address this issue. We've also recently added in this Rottle-Sunderson model, and this is one that we've had quite a amount of success with, I think, in getting good pressure profiles and entrainment in larger scale systems. And it's just an example here is the 8-foot bed from the 2010 PSRI challenge problem, where we get, if you just use like a when you are again without any subgrid correction to it, you can not match this pressure profile very well. You can get a little closer doing some heavy tuning, but, and that's what is shown here with this orange line with, this is like when you are again with a multiplier on it. But then this Rottle-Sunderson looks quite good right out of the box, as we'd say. One, as a caveat here, we are seeing at times using this model, you can see some accumulation of solids on crossovers into cyclones and things like this, where we go, I'm not sure about that, and it's something we are looking further into. If maybe, I think there's a directionality that we need to consider in the with the flow, and or the flow relative to gravity, and whether the subgrid effects are still valid in that direction. So with that, then want to shift to the particle-particle models, and this is the first one I want to talk about is the blended acceleration model. This has been in the code for I'm not sure how long, but a long time, long time, and but we do get questions about it, and basically what's happening here is for a polydispersed set of particles, as they are near close pack, say non-dilute system here, we're going to see say a very small particle or a low density particle next to a larger particle or a heavier particle. They're going to be accelerated. If we just calculate the drag, acceleration due to drag, they're going to be accelerated at quite different rates. However, there's also going to be collisions that are happening, and these are going to be happening at a time scale that is, or say, they're going to be happening at a higher frequency than the time scales that we're simulating over. And so the idea of the blended acceleration model is that it is, as you approach close pack, you see that there's more of a average acceleration of these particles, based on the sum mass of the particles around. And results of this, this is actually one of our test problems that we use, that where this was binary mixture here. Experimental data show you have a pretty good mix of particles throughout, except then at the bottom you start getting some segregation. And with the blended acceleration model on, we see the same thing, whereas without this model, we see a pretty severe segregation. So the question is, should we use it? And yes, I think I have it on most of the simulations I'm running, have it on unless it's very, very dilute, like maybe a cyclone or something, then it's just, you can save a little bit of computational cost. But there's really no downside that I'm aware of to using it. And so then the question is, why is it not defaulted on? And I don't know. maybe it will be. It's coming up enough that, yeah, I think it's probably good to have that on. Next I want to talk about is model we calling, and I agree, this is not really a good name.
We stick with the old name, we add a word to it.
But this a momentum redirection is, so for the MP pick, one of our advantages computationally is that we are not calculating the direct collision of all the different particles, and instead we are modeling, these through a stress that a particle would experience as approaching a region of close pack. And the question then arises, well, what happens to that momentum as particles are slowing down, or which way are they going to bounce off and when experiencing this stress? And what had been in place for a long time in Barracuda, and it's actually still the default, is I think best described as a random scatter. That something's going to happen, they're going to bounce somewhere, we don't know where it is, it's random. But we've been investigating cases where in spouted beds, in some cases where we're just not seeing a lot of participation by particles. There's kind of overly stagnant regions. And it was tracked down to this model. And so we did proposed a different one, which was, I think it's a very reasonable assumption, to say, well, instead of bouncing randomly, they're going to go kind of preferentially in the direction of decreasing stress. and And what we saw with this model is both indeed see a higher participation of particles, more consistent with experimental validation, and also get these nice angle of repose simulation. These are my sand piles here that we did not see with the random scatter model. These piles at times are not very stable, but with this new model, we do see this, and we can. There's a very nice correlation between this momentum redirection parameter, the default, which is roughly, translates to good angle of repose for sand, but we do see a very good correlation with this. So this model was in beta in version 23.1. Was performing well, but didn't see really any downsides to it, only saw upside. It was fully released in version 24, and I think we're making it the default in 24.1. The last thing I want to talk about here is then this bubble breakup and coalescence model. And so we released our discrete bubbles feature in version 23.1, so it had been late in 2023. And I think I talked quite a bit about this in the previous users conference. But when we did release these capabilities, we had no bubble breakup or coalescence model. And it was kind of the big asterisk on this because, there was definitely were cases where, it wasn't important for the simulations, but there's others that we quickly started seeing that, we need to have coalescence, be able to model that to accurately predict the bubble transport, and separations within these systems. So what we've done is we took there's a breakup and coalescence model from this paper by Lair, and set out to implement this. Now the challenge here was that this is a population balance model. And so in it, we're looking at collisions between bubbles with every other bubble in the system. And to have that kind of calculation in Barracuda is going to hurt the efficiency quite a bit. It's kind of a no-go on that. But we were able to do a stochastic implementation of this and get that order of complexity from n squared down to n with some other assumptions about the average bubble that another bubble might be coalescing with. But really pleased with the result here that we're able to have a fast calculation that does pretty nicely represent the breakup and coalescence model here from the population balance model. And this is function of model's function of like velocity, surface tension, turbulence, some other factors, and then also can also be affected by the presence of surfactants. So there is a tuning factor on this. I think the base model we have in there is, I think the experimental data was air in DI water. And so when you start modeling other things like hydrogen and some hydrocarbons and stuff, there is some adjustment that definitely needs to happen to bring the coalescence models in line with any experimental results. But really, this was I think a nice addition that came in I think version 24, maybe. But so this is I'm gonna stop here on. Of the particle physics research that we've been doing. There's certainly much more that has been added to the code since our last users conference. And I'm going to turn it over to Andrew. He's going to share more about the other work that's been done.
Thank you, Jim. I'm Andrew Larson. I'm the principal software engineer here at CPFD. I'm going to talk a little bit about changes since the last users conference that you can find in our software, and then put in my plug for acceleration. Big green play button. So we've been doing this for a while. but we are doing 2 releases a year. We'll do one in the spring, one in the fall, and as Jim talked about, we spend a lot of time with physics, putting in improvements for modeling, also usability, so that you guys can get the job done, and then spend a lot of time verifying that any sort of work we've done to speed up the code is maintained version to version, and then making improvements incrementally along the way to make it faster, to get results quicker. And some of these people have already talked about through the day, so I'll just touch on some of these. So for 22.1, that is when bubbles were introduced, and that came along with absorption model. We have condensation, evaporation. Bubbles can change size due to compressibility, and then work with the drag models. Also, and this one hasn't been touched on, is the tracers were improved, and these are tracers that you can put into the system. They will follow along exactly with the gas flow, and in this way you'd be able to understand what is your residence time of the fluids moving through your system, beyond just there are, particles you could get residence time for a long time, and this really enables looking at the other phase. As far as usability, right, we're consistently working on usability in the GUI for making input easier, more straightforward, and then also, picking out those features that are going to provide the most value. Batch movie has been around for a very long time. Thanks to Sam, and it has been updated from Tickle to Python. Yeah, oh yes, he is in the crowd here. And so batch movie is good for animations, so if you're generating a lot of visualization files, and then you can use this script to generate something that's very fancy. And if you go on to YouTube, I think many of the videos were generated using batch movie. For 23, the big update here is the drag models. Jim's talked about this. I think one of the important things to point out is the change in definition from interstitial to superficial. And so moving to superficial, right, is what is matching in literature. And so if you have literature out there for drag models, this change allows the input of that custom drag model to be much more straightforward, or for those that are predefined and provided, you can make that mapping much easier. The material densities are temperature dependent. I think this is really important for liquids. The secondary feeds, we have GUI stuff, so we have more improvements for usability, for input, and some more kind of usability scripts and output. Again, with this, we would have spent a lot of time to maintain any sort of performance gains that we've had in the past, to ensure that things aren't slowing down as we add new things, which can often be a challenge. 23.1, so more work on the bubbles. Jim talked about that. Drag model. One that hasn't been mentioned is the per species close pack volume fraction. And so this is important. Before this release, you could only specify one value for your close pack volume fraction. With this, now you could have multiple species and say that if you have something that's very granular, that close pack volume fraction is much higher. If you have bigger particulates, you can set it lower, and this then affects how things pack and the different dynamics in the system. And then again, we're just incrementally improving what sort of output is available, getting to the information that the simulations can generate for assessing kind of validation concerns and that type of stuff. Mass and energy. These log files are available and they're very detailed, and they will actually provide information, what's going in and out of your boundary conditions, And then also you could look at system-wide levels of your fluid composition or what solids you have in your system all in one file. And this is nice, so you wouldn't have to do this manually, otherwise in some sort of post-processing step. 424, the graphics here are for the automated plots, and these provide, and this is through TechPlot, this is a macro that provides a lot of basic plots that you'd want to use when you are setting up a simulation, getting things running, and looking at what is your unit doing. And so there's runtime, some flux plane outputs to give you that visibility to know that you need to make a change. Time-varying gravity, this is an interesting one. And so if you have a fluidized bed, gravity makes a big difference. And if gravity is changing, that bed will have dynamics that change along with it. And so there's some particular applications where this is very important and useful. Particle thermal conduction was added. This was kind of the target application there is for fixed bed, and when you have particles connecting, there is some sort of heat transfer that happens as particle volume fraction based. That's the real driver for that one. And then again, we're just, more improvements on stability for evaporation, the model that Jim talked about in terms of physics improvements. So physics improvements, usability, and again, performance is maintained. BC connector pressure feedback. So the BC connectors have been around for a long time. This allows you to take whatever's coming out of a boundary condition and recirculate it back into your simulation. One of the pieces that was missing from that was the feedback you would have from the other end of that connector through pressure. And so if you were trying to connect two units together, the pressure coming back would potentially be very important in terms of what is flowing out from the previous, from the top or not. Okay. I should be a bit better at this part. So, for the hardware, I think the big thing on this slide to take away is that NVIDIA puts in a lot of time and effort to produce new hardware, and they are making really big gains every time. And so if you do have older hardware, you should move it aside, buy a new one, put in a new one, because you're going to get significant gains. I guess here the recommendation is 5 years old, but in general, we have seen just from one generation to the next, sometimes a 2x improvement in performance. And then, of course, that also comes with consistent increases in memory size, which is what's allowing you to run larger and larger simulations. If for some reason, and this has been touched on too, if for some reason you're not able to get access to this hardware or your hardware is old, there are cloud providers that will take your money and allow you to run on the latest hardware. And that's a good way to get extra capacity. And then this would go to any sort of metered licensing, which you all have in your bag. That would be a good use for it. Here is a slide for multiple GPUs. I think one thing I wanted to mention here is we have two operating systems that we support. So if you're running in Windows, there is a hard limit to the size of problem that you can run, and you can only use one GPU. On the Linux side, there is a soft limit to the size of the problem you can run. So if your problem fits inside of the GPU's memory, you're going to run really well. If you exceed it, you can still run. It will still work. It'll run a little bit slower, but that same piece of underlying support is also what provides us to be able to use multiple GPUs to provide even more speed up. And so here, I guess the example is 60 million clouds, and the scaling is respectable. And for this, you can buy multiple licenses for each of these GPUs locally, or again, if you are able to use a cloud provider for acceleration, there's metered licensing options. And I think with that, I will turn it over to Sam.
Okay, great. Thank you, Andrew. Yeah. So I will just touch on a few kind of support and training updates. Some of this stuff might be very old news to some people. Some of it might be kind of new news to others. We definitely strive to provide excellent support, right? So if you're having struggles with Barracuda, don't struggle alone. Please send us an email, and we would be happy to communicate via email, especially with big time zone differences if you're on the other side of the world. But if there is a convenient time to do like screen sharing or something, we tend to do that a lot. Like, hey, let's just jump on a video call. Let's take a look at your setup. Try to figure out to make sure how you can be successful with Barracuda. Best way to contact us, as it has been for a long time, is send an email to support@, and there's probably 6 or 7 of us that see these emails come in. You'll often get a response from Rosemary. She's our most active supporter at this point, but we have a number of people who are kind of available for consultation on more detailed matters as well. We also try to put effort and time into adding articles to the support site. So sometimes our answer on support might be like, hey, we've already written an article for that, or we've already written a script for that, and we'll send you a link to that and hopefully get on your way. Our website does have a search tool, so search for what you're looking for. You might be able to find your answer there as well. As part of our transition to TechPlot away from GMV, this started in 2020. I may be misremembering that, but yeah, basically at CPFD, we are essentially not using GMV anymore. So if people email us with GMV questions, they have to call me because I'm the old guy who used to use GMV, and I try to remember how to use it now. It's getting hazier and hazier. So I definitely recommend that you move to TechPlot if you haven't done so already, because those memories are fading. As part of this, we have tried to create a strong collection of TechPlot for Barracuda videos that shows how to do a number of things. And a lot of times we created these videos as we were learning how to do those things as well. So they should be very well tailored to most Barracuda users. And if you have a specific request of something that you would like to know how to do, then that's probably something that other people would like to know how to do too. And we can always create another video on that. One thing that Niraj and Peter and Shashank have been working on a lot lately is trying to make our collection of publications more robust. And so we're trying to make sure that if Barracuda users are writing articles and publishing in journals, we try to be aware of that, and we have a really strong collection of publications. So if you're looking for information on a specific topic, make sure that you search our website for that as well, and you might find a number of publications that you were just not aware of, where people were already using Barracuda for something very similar to what you're interested in. So just be aware of that. It did not used to be this useful, so I figure some people may not know that that's there. For some things, we own the copyright, so we'll just put a download link directly there. For other things, if we don't own it, if we didn't publish it, we'll just send you to the publisher's website at least, so you can get a copy. If you have publications and you want to be rich and famous, send us your publication, and we will put it on our rich and famous list. New user training. We've tried to do this much more frequently now than in the past. And so if for some of the old timers who came to Albuquerque, you spent 4 or 4.5 days. In Albuquerque, it was like Barracuda boot camp. We don't do that anymore. We found that with the proliferation of web meetings and putting our materials on the website, we can do a training every 1 or 2 months. And so we're trying to make them very frequent. And it takes people about 4 days of half a day to get through kind of the basic training course. And so if you haven't done that, we would invite you to join us for one of those. We also try to be good people and update our training with each release so that when you're on the current release, the training should look like that. Again, if you find errors, let us know, because our goal is to keep it up to date and exactly matching the GUI. If you have new people who are coming into your company, this is really a good way to make sure that they are familiar with Barracuda. They can understand the results that you're showing, or if they're going to be running Barracuda, certainly encourage them to come to one of those classes. Our remaining trainings for this year are listed here. They're also on our website. We have a calendar on the website that shows all these dates. But yeah, if you're interested in joining, please contact us. You can email us at training@cpfd-software.com, and we would be happy to get you signed up for that. Another aspect of training, and these are problems that we do not cover during the new user training class, but I want to make sure people are aware of these. Once you've been using Barracuda for a while and you've been through the new user training, there are a collection of problems that we're calling the supplemental training problems. And these can be really good examples if you're trying to do some specific sort of simulation that you just haven't done before. And sometimes we'll refer people to these and support answers too, because we'll be like, oh yeah, look, that problem covers it. There's a post-processing script that does that. We have a cyclone, an FCC riser, the single cell chemistry, which I appreciate Bruce's plug on because I love that problem. It saves people a lot of time from making chemistry mistakes in terms of unit conversions and all those sorts of things. We have a CFB erosion problem. This will actually be the basis for our advanced training that we'll do tomorrow morning as part of this conference. We have an ebulated bed, which was our first liquid domain training problem. So that has a liquid phase for the domain, solid particles, and gas bubbles all in the same simulation. And then we have our silane deposition problem. And so just a variety of cases that would hopefully be useful references to people when they want to go a little bit beyond the introductory training. There was something else I was going to mention. Oh, training. So tomorrow we're going to do beginning training and advanced training courses. There's not like an official sign up that's required for those. So if you want to participate, please just come to the morning session. And Rescale is going to sponsor cloud-based Linux systems that people can use for that. So if you want to participate, bring a laptop, and then you'll just log into a training machine on your laptop through your web browser. And so if you want to participate, please come to that. And we will be using that CFB erosion problem and the new features that Andrew mentioned in his portion of the talk, where he was saying what had been introduced since our last users conference. That's what we'll kind of be focusing on. We'll be covering, what are those new features? How are they useful? How would you do post-processing to capture the useful bits of information that you can get from that? So if you're a current Barracuda user, I definitely encourage you to come to that one. If you've never touched Barracuda before in your life, I encourage you to go to the introductory training class, and you'll do a hands-on example that would hopefully be a really good introduction and overview of how the software works. So definitely invite everyone to participate in that as well.